Hey friends, this is just a short lesson on capacitors while charging or discharging. So what have we done so far? We've talked about circuits with resistors using V equals IR, complex and series circuits, parallel circuits. So we've done all of our resistor circuits. Then we got into loop analysis. What happens if you have multiple batteries and you're not sure what's in parallel or series? We have multiple currents due to multiple batteries. Then we use a system of equations and a process called loop analysis. The end of last week, we talked about RC circuits, circuits with capacitors and resistors in them, or at least a capacitor. So this lesson continues on the topic of RC circuits. So the most basic RC circuit would be something like this, where I have just a capacitor and a resistor. And I know what's going to happen. If that resistor is a light bulb, when the switch closes, the light bulb comes on. And then as the capacitor charges, the light bulb goes off. So again, switch closes at time 0. If that resistor is a light bulb, it's real bright, and then it goes out as the capacitor becomes charged. This is a very, very simple RC circuit. And what we've talked about so far is the bookends. The problem you had at the end of last week, the solution you just saw in the other video, deals with the bookends. Like initially, what's the current? In this case, it'd be V over R, or E is electromotive force, EMF. That's the voltage of the battery. So whenever you see the fancy E, that's the voltage of the battery. So the initial current for this circuit, when it closes, if the capacitor is uncharged, is E over R. The initial current, V equals IR. The initial current would be E divided by R, and that would be I. But I know my final current is going to be 0. We dealt with the bookends. What's the initial current? What's the current after a long time? Then the switch opens. What's the initial current on the new situation? But we haven't looked at those in between times. What about while the capacitor is charging? What is the current doing? I know it's diminishing, but how is it diminishing? As the charge is building. So the charge is increasing on the capacitor. The voltage on the capacitor is increasing because eventually the voltage on the capacitor is the same as the battery. When the current is 0, that means IR is 0. So the voltage on the battery has to equal the voltage in the capacitor. I know that. We know that. But what's happening on the way? How are we getting there? And so that's what today's lesson is about. It's the first introduction to this, and we're going to dive even deeper into this on day 3 this week, Wednesday. So first off, charge is CV. I wrote it right over here. Q equals CV. The charge eventually for this very simple circuit, the charge eventually stored on the capacitor will simply be its capacitance times E, electromotive force, the voltage of the battery. Q equals CV. When it's fully charged, Q will be CV or CE, fancy E in this case, the electromotive force of the battery. This is just a symbol for the voltage of the battery. How does it approach that? Is it linear? No. What happens is the charge approaches CE. Let's look at this graph. The charge approaches CE, or in this case, the voltage of the battery times C. It approaches that with this function. And it's modeled by this equation. Or I guess the model is the graph, and here's the relationship. Where did this come from? We're going to talk a little bit more of where this came from on day 3. But for now, T is time in seconds. So what is the charge after 1 millisecond or 2 milliseconds? T is the time in seconds. RC. What in the world is RC? RC is multiplying the resistance equivalent in the circuit. Right now, it's just R. If there was 2 R's in series, it'd be 2R. But the resistance equivalent that the capacitor sees times C. This is called tau. It's the time constant. The time constant is about the amount of time, it's defined as the amount of time it takes for the charge to reach about 63% of its maximum charge. There's about 27% left at this point. That's the time constant. It's multiplying R times C. So tau is in seconds as well. And it has to be because I've got time in seconds over time in seconds. This RC is going to be seconds as well, so that I just have a number up there. How do I read this equation? Q at some point in time will be CE or CV, right? At some point in time, it'll be C times the voltage of the battery. E to the negative 0, e to the 0. E to the 0 is going to be just 1. So if you look and I read this equation, at time 0, my charge in the capacitor is 0. Because 1 minus 1 is 0, and then CE, 1 minus 1 is 0. I got nothing. After a long time, after many time constants, e to the negative infinity, when t is really, really long, e to the negative infinity, that's 0. So e to the negative infinity being 0 means that that term in the parentheses is 1. That's what my CE is going to be. So this creates a relationship that looks like this. This is the equation for charge at some point in time, starting from charge. Q equals CV, or in this case, C times the voltage of the battery, 1 minus E to the negative T over RC. If I want to know what the voltage on the capacitor is going to be, it's the same relationship. The voltage on the capacitor starts at 0. It's not charged, and it's increasing. Eventually, it'll be the voltage of the battery, 1 minus E to the negative T over RC. So while I'm charging, the voltage on the capacitor is increasing. The charge on the capacitor is increasing. Is there anything decreasing? Well, yes, current. So if the voltage is 1 minus E to the negative T over RC, again, RC, multiply resistance times capacitance. If that's the voltage increasing at some point in time as it approaches E, eventually it'll be E. Say the battery is 20 volts. This would be 20. And I'm going to go from 0 to 20 with this function. But current is decreasing. I know that I is V over R. So what is during charging? My current's actually decreasing. Well, I should be V over R. The initial current is the voltage of the battery over R, but it's not increasing to that number. It's decreasing. E to the negative infinity is 0, remember? So this, or e to the 0, is just 1. So this function tells me that my current's going to go from E over R to eventually 0. And it goes like this. E over R to eventually 0. And this is E over R, e to the negative T over RC. This is the function. Again, on Wednesday, we're going to dive a little bit more deeply into where this came from. But for now, during charging, this will help you with the homework tonight. Charge, as it increases with time, approaching CV is that function. There's your equation. Voltage is doing the same thing. It's increasing as well, but the current during charging is decreasing. Current's going down, so it's my initial current. You might say it's I naught, whatever I naught is. What's your I naught for the circuit? The initial current, e to the negative T over RC. What about discharging? What if we did in the bookend problems, we charge the capacitor and then we open the switch and let it discharge. When we open the switch and let it discharge, well, here's the deal, guys. During discharging, everything is decreasing. Say I take a charged capacitor. Say I used the battery over here. I charge my capacitor with this circuit, and then I eventually open the switch. So what's going to happen now is I'm just looking at what the capacitor is doing. In your homework, you had a couple resistors over there. So the capacitor is discharging through a couple resistors. That would just affect this. In this case, as the capacitor discharges, everything is decreasing. My voltage is decreasing. My charge is decreasing. Nothing is 1 minus E to the negative T over RC. The current is decreasing. Everything is decreasing. From what? Well, this is where you got to be careful. The voltage is decreasing from whatever the initial voltage of the capacitor was. Was it the voltage of the battery? Or was it something else? If it was something else, whatever it was in parallel with, then that would be the initial voltage on the capacitor as it works its way down to 0. When charge leaves the capacitor and Q equals CV, or V equals Q over C, goes to 0. Remember, the voltage on the capacitor needs charge. What's the charge doing? The charge is going away. That excess of negative charges on one end is distributing out around the circuit to where it'll reach your equilibrium. So my charge initial, what was my charge initial? My charge initial was CV, but whatever that was at time zero when this thing begins to discharge. My current's always diminishing. So during charging, you would have voltage and charge increasing 1 minus e to the negative t over RC, but the current would be decreasing. During discharging, everything is decreasing. Everything looks like some e to the negative t over RC function. When will you use these? What if it says you start with 1 amp of current? How long to get to 1 milliamp? So I got 1 amp of current. How long do I takes to get to 1 milliamp in this thing? Well, again, I at some point in time is I naught e to the negative t over RC. So I'm solving for the time, and I would do 0.001 is going to start at 1 e to the negative t over RC. But again, RC is just the product of whatever your resistance equivalent is and the capacitance that's in there. That could be one problem you see in the homework tonight. The other one it'd be, oh, here's a good one. I'm going to help you with 57 a little bit. 57 says something like, if I am charging, I'm going to help you out a little bit. If I'm charging a capacitor, so say time zero, switch closes, we start to charge. I got R and C. At what point is the voltage on the resistor equal to the voltage on the capacitor? How long does that take? Well, here's what's funky about this. Graphically, the voltage on the resistor is going down. The voltage on the resistor is decreasing because the current's decreasing. The current's initially, I mean, what's the voltage initially on this is E for the resistor. It gets all the voltage. Capacitor has no charge. It's just a wire. But eventually, as the current goes away, all the voltage goes to the capacitor, and then it'll be E. But 57 asks you, hey, when does that happen? What time is that happening? Well, here's the deal. You just got to create your relationships. So I'm going to set this up for you and then let you play a little bit. What's the voltage on the resistor doing? Well, it starts off as E. But remember, it's dropping. So it would be doing something like e to the negative t over RC. Whereas the voltage on the capacitor, maybe I won't write equals yet. The voltage on the capacitor is, call that voltage resistor. It's eventually going to be E, but it's increasing 1 minus e to the negative t over RC. So I want to know at what point do these two equal? Well, set them equal to each other and see what happens. See what happens when, or what time. Again, this is just voltage, right? So that's a constant. That actually probably can be canceled out. At what point do those two equations solve for time? Right? And this can probably cancel. That'll help you with 57. These are the functions for charging or discharging, as current is always decreasing. And during charging, charge and voltage are increasing, but during discharging, everything's decreasing. Hope this helps. That's the lesson for tonight's homework. You've only got a few problems. Knock it out, get it done. Take care. God bless.